We're going to start in on section 9.1. And really all we're going to get into right now, we're not going to talk about actually running tests. We're not going to talk about actually calculating values and things like that. We're just going to talk about the basics. What's the theory behind what we're doing? Okay? So what are the pieces we have to account for? We're going to talk a little bit about how we put them together, but really it's just going to be what does a test look like, how do we make our conclusions, and so on. So the first thing, significance tests. When we run a significance test, what we're doing is running a formal procedure for using observed data to decide between two competing claims. So these claims that we're going to be looking at are what we call our hypotheses. Okay? So you're going to have two claims that you're going to check, and we're going to run through whatever test is appropriate for the information we have, and we're going to decide which claim we're going to go with. It's kind of the basics. That's like to break it down to the lowest level. So an example, a basketball player claims to make 80% of his free throws. We think he might be exaggerating. So we think he doesn't actually shoot 80%. So to test the claim, we would ask him to shoot some free throws and then analyze those results. So we have two competing claims. He's saying he truly shoots 80%. We think he's exaggerating. We think maybe he shoots less than that. So we have one claim that his actual average is 80%, and we have our claim, which is that it's less. So we would run our test based on him shooting a sample of free throws. So he would shoot a certain number of free throws. We'd calculate the percentage of free throws that he makes and compare it to what he claims. Okay, so that's the whole idea behind a hypothesis test. We're looking at these two competing claims. So the hypotheses are those claims. They're working models that we adopt temporarily to test. So we, for the time being, would assume he shoots 80% versus our claim that he would shoot less than 80%. So those are just hypotheses that we take temporarily until we run our test and decide what we're going to do. So there are two different hypotheses to work with each test. Okay? The null hypothesis. So the null hypothesis, which is a term you definitely need to make sure you understand or know, that's the assumption based on the parameter value. So that's the assumption for the population value. The notation is also extremely important. When you write the null hypothesis, it's written as what we say H naught. That's just H with a zero subset there, the H sub 0. Okay? So H0 is going to denote the null hypothesis. So that's the original claim. That's the claim we're making about our population.
So in the last example, is that less than 80%?
No. So in this case, on our last example, the null hypothesis would be his 80%. We're assuming for the moment that he does shoot 80%. We're going to test that claim by having him shoot. Okay? So our population value would be his 80%. That would be the null. Okay? The second hypothesis is what we call the alternative hypothesis. So the alternative hypothesis is the value of the parameter we consider plausible if we end up rejecting the null. So if we decide we have enough evidence to reject the original claim, we would accept the null or the alternative hypothesis in its place. And the notation for the alternative hypothesis is just that H sub A. And the A can be capitalized or not. You'll see it used both ways, so it doesn't really matter as long as you have H sub A. Now, one thing to note, in the definition here it says the alternative hypothesis is the value we consider plausible. But what's going to happen is the only thing we can test based on the way we're going to calculate our values and use them for the test, we can only calculate a range of values. So when we look at an alternative hypothesis, the alternative hypothesis can never be equal to one single value. We're not saying that he claims he shoots 80%, there's our null, we claim he shoots 75. That's not how it works. We can't have a competing claim that's equal to an actual value. The only thing we can do is say it's less than, we can say it's greater than, or not equal to, which we're going to get into in a second. Okay? So when it says the value, it should actually probably say the values of the parameter we consider plausible, because it can only be a range. Okay? So the null hypothesis, every single problem, when you set up the null hypothesis, it is a value set equal to the original claim. So the null is always equal to an actual value. So whatever proposed parameter value is in the problem, that is going to be our null hypothesis. So with our basketball player, our null hypothesis would be that the proportion of free throws he makes. And again, when you're writing these out, you need to make sure you use correct notation. We're talking about a proportion of free throws made. So our parameter is P, the proportion. It is equal to 0.80. When you write your hypotheses, notice the entire notation, because what I have a lot of times people doing is they say H naught equals 0.8. H sub 0 is not a value. It's a statement. Okay? In this instance, the statement we're making is the proportion of free throws that the basketball player would make is 80%. We just don't want to write all that out, so we use notation instead to shorten. Okay? So H sub 0 is a statement. So we separate it and the actual statement with a colon. Do not put H sub 0 equals anything. Okay? It's not an actual value. So H sub 0 says the true proportion is equal to 80%. Is everyone okay with that? So it's important that you understand that, because I will take off. If you put H naught equals, even if you say H naught equals P equals 0.8, that's wrong. HO, or H sub 0, is not an equal value. Okay? So make sure you get that part. Now, the alternative hypothesis, like I was just talking about on the last slide, there's no way for us to gauge what the actual value would be if it's not 80%. There's nothing that we would be able to find that would say, if 80% is wrong, then this is definitely going to be our value. Okay? So the only thing we can test with an alternative hypothesis is either we're going to be less than the proposed value, will be greater than the proposed value, or we will just not be equal to. Sometimes we might not have an inclination which direction it's supposed to go. So our claim would be like 80% here. If we don't have any idea of whether he should be shooting less or more, then we would go not equal to. We know, we just want to say it's different than 80%. So it might be more than, it might be less than. We don't know just from what we're looking at.
How does that work again?
So if for whatever reason, as you're reading the question, a lot of times you'll have an idea that if this is the claim, we think the actual value is going to be less than that. Or we're going to look at it and we can see that it should be greater than that, right? That's going to be what we test against. But there are times where we might not know which direction it's supposed to go. So here's our claim. We don't know if it's supposed to be higher or lower based on what we see. So then in that instance, we'd have to say just not equal to. We know it's not 80%. We just don't know which direction it's going to go from there. Does that make sense?
So if you can't tell for sure, you just wanted to go not equal to, or just guess less or greater. Like if it doesn't tell you.
You want to go not equal to. If you can't definitively say it's going to be more or less, you got to go not equal to, because then it runs a little bit differently than the less or greater than. Okay? So yes, if you don't have an inclination on which direction it's going to go, not equal to is going to be your choice.
The problem will give you like the simulation or whatever, or
Yeah, they'll give you the sample values then too. And the problem though is, even though they might give you a value, so they give you the p is equal to 0.8, they might give his sample value as 76%. Now, even though that's lower, that might just be a sample that happened to be lower, because we know if we do random samples over and over, sometimes we might be higher, sometimes we might be lower, and so on. So we can't base it just on that alone. We have to run through our test to see which direction it actually goes. Okay? So, if we think our player is exaggerating, what would our alternative hypothesis be? Less than 80%. So we would write that as H sub A, colon, so the statement is his true proportion of free throws made would be less than 80%. So with every hypothesis test you run, your first step is going to be to state these hypotheses. What's the claimed value, so what's the null? And then what's the alternative hypothesis that we accept if we end up rejecting the null? So this is what the notation will look like. You just put these two next to each other, or null hypothesis and then alternative hypothesis below. Okay? So the claim's that it's exactly 80. Our claim, what we want to see if it happens, is that it's less than 80. Okay with that idea? Okay? So hypotheses, very important to make sure you know how to set those up first. So those are going to be ones that you have to be able to read through the problem and pull out the information to set those up, because those dictate what we do with the rest of the text. Okay? Now, the hypotheses should express the hopes or suspicions we have before we see the data. If we run all of our information first, we can make our information say whatever we truly want it to be. So we have to have selected our hypotheses first before we start doing anything with the data. Okay? So you always make sure you do that first. Now, with the alternative hypotheses, there's two different types to deal with. And they run a little bit differently. For the most part, a hypothesis test is a hypothesis test. It's the same process over and over. But the alternative hypotheses will dictate a little bit different process depending on what we're going for. So, a one-sided alternative hypothesis is one where we are stating greater than or less than. So when we state our hypotheses, we are picking a direction. We don't think it's 80%, we think it's less than. We're choosing one single direction. So we have a one-sided alternative hypothesis. Or our claim was 80%, we think it's actually higher. So we're picking one direction. That's a one-sided alternative. But we said in some cases we might not have an inclination as to which direction it's going. So if we think it's not equal to, so he says it's 80%, we don't know which direction it's going, we just think it's different than that, that would be a two-sided alternative. Now we have to look at both sides, both less than and greater than. So in the problems, what you're looking for are some key words. Usually, they'll tell you one direction or the other, or they'll use the phrase different from. So if they say the alternative hypothesis less than, that means you're doing a one-sided alternative less than, or greater than, one-sided alternative greater than. But if they don't give you a direction one way or another, most often they'll say something like, show that, or run a test to see if the alternative is different than the null. So then that means you're going not equal to, and then you run it a little bit differently. We okay with that? Okay. Now, when we think about a hypothesis test, so before we get into the meat of this, the way a hypothesis test works is kind of like how a jury works in a trial. Okay? So we have a claim that we're saying this is true for our population, and we're going to run a test to see if that claim is true or not, or see if we have enough evidence to state that it's true or not. Okay? So the way a jury works, if we want to prove someone guilty, so anytime you go to court, for whatever reason, the jury is also always instructed to assume what? That you're innocent. Okay? You're innocent until the prosecution proves you're guilty, right? So the assumption is the person, the defendant, is innocent unless we have enough proof to say that they're guilty. Okay? So our null hypothesis would be that the defendant is innocent. That's how they start off the process, and they stay innocent unless we have facts that make it unlikely beyond a reasonable doubt. So we have enough proof to say, well, that innocence claim is not true. We don't believe that. We're going to find him guilty instead. Okay? So we have a claim, and that claim stays throughout the process until we have enough proof to say otherwise. Does that make sense? So if the prosecution can put enough evidence in front of the jury that they decide, well, the claim of innocence no longer makes sense, we're going to accept the alternative, which is that they're guilty. Everyone okay with that idea? So the hypothesis test is going to be the same thing. We're going to keep our null hypothesis until we decide we have enough evidence to reject it in favor of the alternative. So that null hypothesis is the truth until we can prove it otherwise. Okay? So that's kind of the way we're going to attack these hypothesis tests here. So, statistically, the way we're going to run our test is going to be using normal distribution calculations. You don't have to write this. So you're going to be working with a normal distribution again. Finding z-scores, looking up z-scores to find what we call p-values or probabilities. Okay? So, when we work with these normal distributions, the p-value, this you do want to write down, the p-value is going to be a value we calculate to determine which hypothesis we end up going with. So what the p-value tells us, it's a conditional probability. It's the probability that our findings would occur given that the null hypothesis is true. So remember, throughout the entire test, we're assuming that null is true. Even if we feel like it might not be, we have to assume it is. The p-value will then tell us whether we stick with the null hypothesis or whether we can reject it in favor of the alternative. So another thing I want you to add with this, when you find a p-value, it is a conditional probability. The condition is the hypothesis is true. So what's the probability that we find this sample value? What's the probability we find this sample proportion? Or what's the probability that we find this sample mean if that null is actually true? Okay? So if we think about this, if a p-value is high, so if I get a really high p-value, if I get a high percentage or high probability, then what we're saying is we didn't find anything unlikely. The probability that this sample value occurs, given that the null is true, if that's a high value, it means it's a high probability. It means it's not anything unusual. And if it's not unusual, then that means we didn't find any evidence to reject the null. We didn't find anything unusual about claiming that null value. So, when you have a high p-value, the phrase you use, and this is important, I want you to circle or highlight or star or whatever you need to, this phrase right here. When you make your conclusion for your test, you would say something to the effect, since the p-value is so high, we fail to reject the null. And it is imperative that you use this phrasing. When you fail to reject, you are not proving that the null is true. So when we make that null hypothesis, we're assuming it's true, but our test cannot prove that it's true. So if we find a high p-value, that means we didn't find enough evidence to reject that null. We can only fail to reject that null. All we can say, the strongest conclusion we can make, is that the null doesn't appear to be false. So when you run this test, you will never be able to say that that proves the null hypothesis is true. It cannot happen. The best we can say is it doesn't appear to be false. It doesn't appear to be wrong based on our findings. Okay? So again, when you draw that conclusion, since p is so high, we fail to reject the null. And then you would say something to the effect, there's not enough evidence to support the alternative, or however you want to say that, and we'll get into that when we go to our problems later on. We okay with that? Okay. What that also means then is if we get a p-value that's low enough, and the key word here is low enough, it means that it would be very unlikely for us to find this particular sample value if our null is actually true. So if that null hypothesis is in fact true, the likelihood of us finding this particular sample is extremely rare. Which means we can now reject the null. The fact that we found something that really shouldn't have been found leads us to believe that the original claim was not true like we assumed to start. We're going to talk about that. Okay? So we're going to talk here in a second about what low enough means. So if you find a p-value that's low enough, you would reject the null. You're saying that we don't believe, we just happen to find this rare random sample by chance alone. So we think that the null is wrong, it has to be something else. Otherwise, there's no way to explain us getting this value that we got. Okay? Now, when you do this, when you get a low p-value, you do actually have two options. You could decide that you just happen to grab a rare sample. Okay? There is that possibility that you did happen to grab a sample that's way off from the normal path. But the probability, the likelihood of that occurring most often means that the null couldn't have been true. Okay? So when you get that low p-value, you could say that you just grabbed a rare sample, in which case you probably want to go out and grab another sample just to see. And if you get another rare sample, you can probably be sure that null is definitely wrong. Okay? But when you do these types of problems, when you draw your conclusions, one of the things you always need to do is report your p-value with your conclusion. Because what you think is rare might not be rare to someone else looking at that same research. Or what you don't think is rare might be rare to someone and they decide to reject when you didn't, and so on. Okay? So you always need to write or put your p-value with your conclusions. Now, the question is, how small does p need to be before we start rejecting the null? And that's a tough question. This is where most of you are going to hate this particular section and chapter. It's context dependent. Sometimes a p-value might be low enough to reject. Other times that exact same p-value is not enough. So you have to think about the scenario as a whole. if you make a claim to that null hypothesis, if you want to be absolutely certain that that null is wrong before you reject it, that means you're going to require a very, very small probability. If you're not that concerned with being absolutely certain that it's wrong before you reject it, then you would accept higher probabilities before you, or to reject that or that very same null. So you have to think about the question itself, the scenario, as to which p-values you want to use to reject and which ones you choose not to reject.
And will the questions be set up to tell you what side you should be on?
Yes, and we're going to talk about, because this whole subjectivity is kind of tough. Like, I think it's low enough that I'm going to reject. Some people say, well, that's not low enough, I'm not going to reject. So you kind of get into that issue. We're going to talk about making an absolute point. We're going to say this is the point we're going to look at. If we're less than it, we're rejecting. If we're not, we're going to fail to reject. And we'll talk about that here in a second. So, like I just mentioned, anytime you draw a conclusion based on a t-test, or a hypothesis test, you need to have the p-value accompanying it so others can make the same decision. Now, the other thing you should do is whenever you run a hypothesis test, you should always run a corresponding confidence interval to show the size of the effect. If you decided that you rejected the null, so our free throw example, the claim was 80%, we think it's less than 80%. If we ran that test and we rejected the null, so we said that 80% is wrong, it's got to be less, we would create a confidence interval to show where the new hypothesis should be. So what interval of values would be plausible for his actual free throw percentage? Okay, so if you reject that null, make sure your p-value comes with it. Make sure you also have a confidence interval so you can show how big of a change is being made. Okay? Now, like we were discussing, the subjectivity of this idea. Well, I think it's low enough to reject. Another person might say it's not. So, the way we kind of account for that is we create what we call alpha levels. So alpha levels sometimes are called significance levels, but we choose these values to make an absolute decision. So there is no question of should we reject or should we not reject. We're going to set a value and say this is the cutoff. If I'm above this, I make this decision. If I'm below this, I make this decision. That way there's no ambiguity. There's no way for you to decide that your data says something it doesn't. Okay? So, when we say rare, when we have that p-value that's low enough, we are going to set a threshold for the p-value arbitrarily. You're going to pick. Now that choice has to be made before you run the test. Because like we said, if you have a value in mind, if you have a conclusion you want to find, you could run the test and then make the conclusion based on whatever you find. And then at that point, you're not even doing anything. So if you know you want to reject the null, even if you get a high p-value, you might say, well, in this case, I think that's low enough, I'm going to reject. When in actuality, you probably shouldn't. Or another time where you don't want to reject the null, you're going to say, well, that's not enough information. We're going to assume the original. So you arbitrarily pick. What threshold do I want? How certain do I want to be before I reject that null? Okay? So what we do is we create what we call alpha levels. You're going to pick a threshold for your probability. Okay? And we denote our alpha levels with the letter alpha. So, picking your alpha level. And one of the things that's also going to kind of bug you guys about this chapter is your idea of percentages. When we say these probabilities, these p-values, if I were to give you a probability of 5%, would you guys say that that's unusual or not? Yeah, if you were playing a game of chance and they said you have a 5% chance of winning, are you likely to play that game? Not really. But one of the things you have to get rid of is your preconceived notion of percentages. Most of you base your percentages off of grades, right? So like you need high percentages, otherwise they're bad. I mean, in some cases, in most of your cases, like a 50%, 60%, 70% are horrible, absolutely atrocious percentages, right? So that's not the case in these. All right? When we're working with these, very small percentages can be not unusual. If you think about the way that a normal distribution works, we said that in general, about 2 standard deviations becomes unusual. But at 2 standard deviations, we're still usually up in the 3 to 4% range, which means we're not unusual at 3 and 4% sometimes. Okay? So you got to kind of keep that in mind when you're looking at these values. So for these alpha levels, if our p-value, so if we calculate our p-value, we run through our test, we've calculated all of our values, and our p-value is less than alpha, then that means we want to reject the null. If we have a p-value less than alpha, that means we were unusual enough that we no longer believe that original claim.
So we just pick anything that we want to pick.
Well, we're going to talk about that. Okay? When we say it's picked arbitrarily, it's a little more involved than that. I mean, it's got to be something that's actually useful to the problem. So we'll talk about the main types, and in most cases, the problem itself is going to tell you. It's going to say, this is the alpha level we're using.
I was going to say, for like the basketball, you say 50%.
No, that's way too high.
That's too high.
That's way too high for an alpha level. For alpha levels, we're talking like, when we talk rare, when we talk unusual, we're talking like down in the 1%, in the 2, 3, 4, 5% range. So we're talking really, really small probabilities, okay? So if our p-value is less than that threshold we set, we reject the null because we're saying our results were statistically significant. We don't believe we happen to grab this rare sample by chance. It means that our sample is probably not very rare. It's just that our center was off. We didn't have the correct starting point. Okay? Now, what that also means then on the flip side is that if our p-value is greater than our alpha, we would fail to reject. Now, when we talk about these alpha values, the common levels are 0.1, 0.05, and 0.01. So 10%, 5%, 1%. You will not, that I've ever seen, you will not ever see an alpha level above 10%. Okay? Though that's about as high as you will ever see it go. A 10% alpha level means they really don't need a lot of evidence to reject the null. They don't need a lot to see that they're going to reject the null in favor of the alternative. Okay? The lower the alpha level, the more evidence you need in order to reject that original claim.
So if it's greater than it appears to be false.
No, so if it's less than, we reject the null. We say the original claim's wrong, we're going in favor of the alternative. If our p-value is greater than, then we go with the original. Then we say we don't have enough evidence to suggest that it's false, we're going to stick with the original.
So if it's the alpha level, the kind of like difficult to get the test time?
Actually, the alpha level is dependent on how sure you want to be that null is wrong. So how much evidence do you have to have before you're willing to let go of that original claim? Okay? So it's something that, like I'm trying to think, the bolts that hold planes together. Okay? Now, when they do that, they have to test the shear strength. So how much shear force can a bolt withstand before it snaps and falls apart? Okay? So if they say that in order to hold a plane together, the mean shear strength has to be a certain value, and you test a sample of bolts on their shear strength, how certain do you want to be that that original claim is true before you reject? Very. Because if you're going to throw bolts in there that aren't to specs, you're risking people's lives at that point. So that would be one, you would choose an extremely low alpha level. In order to get rid of that null hypothesis, you want to be absolutely certain that it's wrong. Does that make sense? But if it was something else like the mean number of pepperonis on a pizza, okay, in that case, we could reject or not reject that null. It's not that important. So we'll see a higher alpha level because there it's not like a life or death thing. So those alpha levels, like I said, in most cases, you guys aren't going to be dictating those yourself. I'm not going to have you try to come up with this would be an appropriate alpha level. The problems we're going to work with, they're going to tell you. This is the alpha level we want to work with, and then run the test against it. Okay? But if you were doing this in the real world, you would have to think about those things to pick your alpha level.
Is it ever where it can be 100%? Or like where it has to be 100%?
No, I doubt it. I think there's got to be something. The other thing, like I said earlier, you have to choose your alpha level before you perform your test. Because again, if you have a certain conclusion in mind, you could run your test and get a p-value and then say, oh, well, I'm going to set my alpha level this way, so then I can reject, or then I can fail to reject. So you have to have it done beforehand so you can't mess with the results. Either you're going to reject or you're not based on the level you chose. Okay? So here's where I was trying to get to before I forgot I had it so far down the list. If your p-value falls above alpha, we fail to reject the null. Again, I want you to highlight that. Fail to reject the null. Do not ever say we accept the null. When we run a test and we fail to reject, we are not saying that the null is true. We're simply saying we didn't find evidence to show that it's false. So when you run these, our goal is to show it's false. And either we do or we don't. So we're never going to say the null is true. We can only say we found the evidence to say it's false, so we're going to go with the alternative, or we say we didn't find enough evidence to say it's false, so we continue to go with it. Okay? So we're not accepting it, we're just failing to reject it. Okay. So, here are the problems I want you to try out.